spoke about rotational variables, equations of rotations. We spoke about how to look at a translation from, linear variables to rotational variables. And in continuing with what we have been doing, we shall continue with other stuff that we did for linear variables and look at how they are treated on rotational variables. So section 10-4 is on the kinetic energy of rotation. Now we know for linear variables, something that's moving just in a straight line, it's k equals half mv squared. Simple enough. Now, if I want to calculate half mv squared for something that is rotating, can you tell me how am I going to do that? Now, I have a rotating body that is extended, not a single point. Okay.
Kinetic energy.
Yeah, I want to find the kinetic energy. Now, it's half mv squared. The problem is which m? Okay, I can find the total mass, for example. That's one solution, fine. But then, in the previous lecture, we found a peculiar problem because v here is the translational or tangential velocity. And we found that the velocity for each point is different depending on its radius. We found that things that are further away from the center appear to be faster in tangential velocity than those closer. So which v do I put? This gives me a problem. Now, one thing I can do is I can find a billion points and start adding. Half mv1 v1 squared plus half m2 v2 squared plus half m3 v3 squared, etc. But that would give you a very, very large sum of mivi squareds, and which would very, very quickly become unreasonable of us to do because if you have something physical, then you have a huge number of points to take or an infinite number of points to take. So we need to find a different approach. Luckily, we know from the previous lecture that v equals omega r. Ha. Okay. Then perhaps what I can do is translate. Perhaps what we can do is translate. V equals omega r. So I will substitute that. Now my kinetic energy is half mi omega ri squared. Okay. I can rearrange that because omega is a constant, right? So I can take omega out. The half is also constant. I can take it out. I end up with half omega squared, طلعنا برا, sum of mi squared. Do you remember what is the sum of mi? Miri? You should, considering that your quiz on chapter 9 is today. MIRI over M is your center of mass. Okay. But now we have something different. We have MIRI squared. And that, we define it, we give it a new name. We call it I. It has a unit of kilograms meter squared. And it is what we call rotational inertia or moment of inertia. Okay. So we have redefined kinetic energy to be half I omega squared instead of mv squared. So just like we translated v to omega, we sort of, it's not exactly the same, but we sort of translate m to I, where I is mi/ri squared. So if I have a ball that's moving like this, it's half mv squared. If I have a ball that's going in a circle, then it's half I omega squared. And we add one more thing to our table here, which we used in the previous lecture. M goes to I. So when we defined M, if you remember at the very beginning of the course, we defined M by saying we have F equals MA. So we said M is how much there is resistance to a force. And in a bit, we will describe I is how much resistance we have to a rotational force, which we call a torque. Okay. Now, if we have a group of particles, then finding I is easy. It's sum of mi/ri squared. But what if I have a real object? Say I have a pen in my hand, or a calculator or a book, something physical. How do I do with them? How many points do I take? Now, naturally, the more points I take, the more accurate I become. But NON, what's non, Mariam? What do you mean by non? Now, I can take an infinite number of points to get the most accuracy. And an infinite number of points is always called integration. I equals the integration of r squared dm. So mi/ri squared or integration of r squared dm. I hope you're writing this down. So how do I calculate this rotational inertia? Well, if I integrate equation 1033, which was this, over a continuous body, I can calculate the rotational inertia of any object whatsoever. Now, in principle, we can always use this equation, but integration is not nice and it's not easy. I think we all agree on that. And there are some shapes which are quite common and that appear in everyday life over and over again. So for these, the values have already been calculated in your book, for example, table 10-2, for common axes. Yeah, because we have R, and R means it has to do with a specific axis. If this is the center, then this is R. But if I rotate about this point, then my R's will be very different. Okay. For example, hoop about a central axis is mr squared, where r is the radius and m is the total mass. Annular cylinder or ring about a central axis, half m r1 squared plus r2 squared. And you have a whole bunch of these in your book, and of which a copy will be supplied in any exam. So we have all of these that we can use. They are ready-made. We don't need to calculate them from scratch. Any questions so far? Okay. Then let's do a PIQ to see if we have truly understood what we believe to have understood. PIQs under today's lecture. So, figure below shows three small spheres that rotate about a vertical axis. You have the mass, you have the r from the rotational axis. Rank the three spheres according to their rotational inertia about the x-axis, about the rotational axis, from biggest to smallest. Two minutes. Okay. Yep, pretty much everyone got the right answer. And that when we put in the numbers into MIRI squared, we actually end up with exactly the same number for all of them. So 36 times 1 is 36. 9 times 2 squared, 9 times 4 is still 36. And 4 times 3 squared, 4 times 9 is still 36. Which tells us something very, very important. That we can have, with rotation, unlike just translational problems, we can have the same I for different configurations. Yeah, it means that to rotate something lightweight but at a longer radius is just as difficult as rotating something heavy at a short radius. So, I mean, think about what this problem says. It says if you have something that weighs 36 kilograms and you're trying to rotate it with 1 meter radius, and if you have something way lighter, just 4 kilos, which is nothing, but you're trying to rotate it at 3 meters, it is exactly the same problem. It's just as difficult. Okay, everything we have done so far has been rotating with respect to the center. What if I am not rotating to the center? I am rotating with respect to something on the side. Okay, like we usually do with papers or, with erasers or something like that when we're playing. I'm rotating with respect to a side, not with respect to the center of mass. Now we have two options. Option one is to calculate it from scratch, I equals sum of mi ri squared or integral of r squared dm. The other option though is, wait a minute, I already have that nice table that gives me what is my I with respect to the center of mass. So I have a rule here. I have my I with respect to center of mass. I find where do I want to rotate it with respect, and I find the perpendicular distance between them. And then I have this equation. I with respect to any axis is equal to the I of the center of mass plus the mass of the object, total mass, times the square of the distance between the two axes. Okay? And this is called the parallel axis theorem. As long as these two axes are parallel, there's no angle between them, we can apply this. Let's do a sample problem. What is the rotational inertia about an axis through the center of mass perpendicular to the rod as shown? Well, center of mass is going to be right in the middle. Mi ri squared. Each one of them is half the length away. So I have m half L squared plus m half L squared is equal to half mL squared. That is at the center of mass. But. What if instead I don't want to do it about the center of mass, I want to rotate it about the end? Now what is the rotation inertia of the body? Now I can do mi squared again, but instead I'm going to use the parallel axis theorem. About the center of mass, it's half ml squared. And I'm going to add to it, the total mass, 2m, multiplied by the distance of the movement, half L squared, and I end up with mL squared. Which, if you do the mi squared, you will end up with the exact same result. Let's try this. Let's try another problem. Consider two masses, each of size 2m, at the ends of a light rod of length L, with the axis of rotation through the center of the rod. Now we double the length of the rod, but halve the masses. What happens to I? Is IA bigger than IB? IB is bigger than IA, or are they the same? Go. Let's see. An overwhelming majority of students chose IB is bigger, which is indeed the correct answer. So if I do for this one, I will have 2m L over 2 squared times 2, which I will end up with 2m L squared over 4 times 2, which is ml squared. But here I will have ml squared plus ml squared, which is 2ml squared, which means IB is bigger than IA. Although the masses are smaller, the greater distance makes it more difficult. Okay. Now, this is a nice problem in your book, which shows you the effect of rotational kinetic energy if not accounted for correctly. Now, you see this mess in this photo? This is a real photo. Okay. And what happens is, this was a system that checked for failures, for probable failures in industrial components. So in 1985, Test Devices Incorporated was spinning a testing sample of a solid steel rotor that's shaped like a disc with a mass of 272 kilograms and a radius of 38 centimeters. Now, when the sample reached an angular speed of 14,000 revolutions per minute, so 14,000 RPM, okay, there was a thump from the test system and everything went off. They went to check and they found that photo. Okay, it was a mess. Things were broken. It was a nightmare. Yeah. Some stuff, a door, for example, from the room had flown out of the window all the way to the parking lot being lodged in a car. Okay. Now, this is what an industry is called a disaster. I mean, the damage was huge. Okay. And the question is, how much energy was released in the explosion of the rotor? So we know that K equals half I omega squared for rotation. This is a disk. So 270 mass 272 kilograms, radius 38 centimeters, omega of 14,000 revolutions per minute. First thing first, I need to convert my omega to SI units. So I convert revolutions to radians, multiplying it by 2 pi. And I convert minute to seconds, so divide everything by 60, and I end up with 1.466 times 10 to the power 3 radians per second. Then I need to find the moment of inertia. From that lovely table of ours in the book, I can find for a disk spinning around its center, it's half mr squared. I end up with a moment of inertia of 19.64 kilograms meter squared. Half I omega squared gives me 2.1 times 10 to the power 7 joules. That's a lot of energy. Okay. Now, usually I do a demonstration about this in the lecture theater, but unfortunately, that's not possible now. So we'll have to make do with pictures. Whenever we open a door, whenever we open a door to, a room or a lecture theater or whatever, sorry. We tend to push it usually from the doorknob. Now, find the strongest person you know and make him a bet or make her a bet. I am going to give you 1 million riyals if you can open the door by pushing it at the hinges, by pushing it here at the hinge. Make it rotate. Don't break it off. You have to make it rotate open, but by pushing it over there and not over here. And I can guarantee you you're not losing 1 million riyals. Okay. Now you have a hinge usually here and you want to open the door. You push with the same force on 3 different positions. Now from experience, okay, and then you say, okay, you know what? For the fun of it, I'm going to try to make it rotate by pulling it in that direction. Okay. Now from experience, you will find that the distance from the axis actually matters. So I am going to name those F1, F2, F3, and F4. From experience, you will find that F3 is easiest to open the door. F2 is still possible, but more difficult. And F1 is almost impossible unless you push it really, really hard. And well, F4 is just impossible. If you're pulling it in that direction, there's no way it's going to rotate. Why? Newton's second law for things that move in straight lines and stuff was F equals ma. Now force, we have translated everything into rotational stuff except force, so it's time. For rotation, we call it torque. Now what is torque? Torque is the quantity that indicates if I am pushing or pulling with some force F, how much rotation do I get? Okay. Now, say I have this force at an angle over there at radius r. My line of action, so if I extend the force, is going to be that dashed line. And what I call a moment arm is the distance, the perpendicular distance between my line of action and the hinge or the fulcrum. Okay. And turns out my torque is given by R cross F. Remember that nasty cross product in chapter 3? It's back to haunt you. Sorry. So RF sine theta or R cross F. Now, whenever I am having a force that is perpendicular, at an angle, I have two components, a parallel component and a perpendicular component. Now, the perpendicular component is going to cause the torque by R of sine theta, and the parallel component does not do anything because what's the cross product of two parallel vectors? Just zero. As usual, counterclockwise, positive, clockwise, negative. Let's do a few examples. Torque equals RF sine theta. If I am pulling it to the right, what is my torque? Yep, RF sine theta, not only RF. And we end up with the same angle. The angle is zero, so my torque is zero. What if I have something perpendicular? Then my theta is 90 degrees, so my torque is going to be maximum torque, which is simply RF. Now, what if I am pushing at the hinge? It's still perpendicular, but I am pushing at the hinge. What's going to be? Sorry, just a second. Sorry, I'm disconnected from the other one. That is where I see the chat session. Just give me a second to reconnect. Okay, I'm reconnected. And yep, we have a whole bunch of zeros, which is correct. Yeah, we don't end up with actually any movement. We don't end up with any movement simply because although we are pushing perpendicularly and with some force, our distance is 0. And since we have RF sine theta and R is 0, it really doesn't matter what F or sine theta is. We are still ending up with 0, which is why I told you, you can bet 1,000,000 riyals and you're not going to have an issue. Any questions so far? Let's do a few PIQs, if there are no questions, to jog our memories and, get it really into our system. So, next question. You are using a wrench and trying to loosen a rusty nail. Which of the arrangements shown is most effective in loosening the nut? So which one of these arrangements will make it easiest to move it? Okay. Let's see. Most people chose option B. Actually, pretty much everyone chose option B, I think. I know we have a couple of people who chose other options. Okay, but most people chose option B, which is the correct option. I mean, option 1 will give you RF sine theta. Will give me RF sine theta. Theta is 90 degrees, so just RF. Number 3 will give me RF sine theta, which is already less than 1. Number 4, yeah, this will be my line of action. So it will be different R, F sine theta. But number 2 will give me R plus capital R, F sine theta, which is the biggest number that I'm going to get. Which is why if you have ever seen, لما تغيروا الغاز في البيت مثلا, or in industrial situations, you will see they are using really, really large wrenches, really long wrenches. It's not because they love using heavy equipment, it's because it just makes it really easier to twist things around. Okay, let's do one last PIQ. An object with a triangular cross-section is free to rotate about the axis shown. 4 identical magnitude forces are exerted on the object as shown. Which one of these, if any, exerts the largest torque on the object? Okay. Let's see. Majority of people chose number 3, which is indeed, let's see. Yep, 67 people chose it, and it is indeed the correct answer. So this one, this is my R, and this is my F. So it will give me RF sine theta. This is a shorter R. F is at an angle, RF sine theta. This is right. Your theta here is 0. So you will get 0 force. But this gives you the longest radius and an almost perpendicular force. So it will give you the highest torque by far. Okay, and amazingly, for a change, we have actually finished a lecture early by completing all of the slides before the end of the lecture time. So, yay! Do you have any questions? Salim, is that a yeah for, yay, we finished the lecture, or yeah as in, yeah, we have questions?
No, Doctor, no questions.
Okay, so if we don't have any questions, we call it early. We finished the lectures 10 minutes early. أذن الظهر، خلصنا مع أذان الظهر بالضبط. فتقبل الله صيامكم وأعمالكم. Let's go pray. وإن شاء الله الكويز 7:30 بالتوفيق فيه. It's all multiple choice today. So good luck.